Ladies and gentlemen, welcome to our third lesson in our new flipped classroom series. We're going to do some crazy factoring today, a totally brand new method called factor by grouping. And our key definition today, right here, we're going to say that this is a method we use to factor polynomials with 4 terms. Now, unfortunately, we don't have a fancy name for polynomials with 4 terms. Polynomials with 2 terms, we call it a binomial. Polynomial with 3 terms is called a trinomial. And perhaps one of you guys out there can create a new fancy name for a polynomial with 4 terms. The key concept today is going to be GCF. It's all about being able to identify and factor out a GCF. And if you're comfortable pulling out GCFs, then you're going to really like this method we call factor by grouping. Now, with this in mind, what I'd like to do before we actually tackle a brand new problem today, I'd like to warm up with just a couple of older problems that involve pulling out a GCF, just to get us warmed up and talking about finding that greatest common factor. Okay, as we warm up with identifying and factoring out our GCF, let's take a look at this problem. 8x to the 4th power minus 12x to the 3rd power. And we're just asking ourselves, both of these terms are divisible by what? I would say they're both divisible by 4x cubed. If you're having trouble with your exponents, a little, I guess an idea that's safe to go by is you just pull out the term with the smallest exponent. You'll notice between these two exponents, 3 is the smallest one, so I pulled out x cubed. Alright, now here comes the fun part, deciding what's left over after we factor out that 4x cubed. And I'm going to switch over here to my orange pen. Now, what I'm about to write in orange, you do not have to write per se. But I would just want to emphasize that when we factor out that 4x cubed, we are dividing this term by 4x cubed. And the same goes for the second term. We are now dividing him by 4x cubed. Switch back to another pen color here. Okay, so 8 divided by 4 is going to give me 2, and x to the 4th divided by x cubed is going to give me x. Again, remind yourself when you're dividing the x's, when you're dividing like bases, we're going to subtract the exponents. 4 minus 3 gave me an exponent of 1. Minus 12 divided by 4 is going to give me 3, and then of course x cubed divided by x cubed is just 1. 3 times 1 is 3. So there is our first answer, factor with a GCF. Let's try one more of those. Number 2. If I gave you 6x cubed minus 4x squared plus 10x, can we identify our GCF? All 3 terms are divisible by what? I would say the biggest term they're all divisible by is 2x. If I divide the 6x cubed by 2x, I'll be left with 3x squared. If I divide the middle term by 2x, I'll be left with, well, 2x. And last but not least, if I divide the 10x by 2x, I'll be left with a plus 5. And that is my final factored answer. We would ask ourselves if we could factor this trinomial here any further, perhaps with a guess and check method, but I did not have any luck doing so, so we would say that this one's factored completely. Well, after that little warm-up with just pulling out a basic, simple GCF, we're ready to rock and roll today and tackle our new topic, factor by grouping. Our directions for this problem are to simply factor completely, and I'm going to present you with the polynomial x cubed minus 7x squared minus 4x plus 28. So you'll notice we do have a polynomial with 4 terms, and that was our theme today. And we ask ourselves, well, first of all, do all 4 terms have a GCF? And I got nothing. I cannot think of anything that all 4 terms are divisible by. So, but what we do have here today, you'll notice, let's just limit ourselves to the first 2 terms. If we look at just these first 2 terms, do they have a GCF? And I would say that both of those first 2 terms are divisible by x squared. Okay, So we're pulling out a GCF from just the first two terms. If I divide the first term by x squared, I get x. And if I divide the second term by x squared, I get minus 7. Okay. Now shift your focus to the third and the fourth term and ask yourself, do those two terms have a GCF by themselves? And you could make the argument that their GCF is 4. I'm going to make the argument that that the GCF's a negative 4, and I'll point out here in a second why that's helpful. So if I divide the first term by negative 4, I'll get positive x, and if I divide that last term by negative 4, I'll get minus 7. Now, why was that important to pull out a negative 4 instead of a positive 4? Well, one of the keys here is that I want to point out is that this binomial in here and this binomial over here, they should be exactly the same. These should be perfect matches right here. If they're not, that's an indication that we did something wrong on this method. Okay, now we're just getting warmed up. I would say we're about halfway through the problem. And now I want to ask you, okay, does this term right here have anything in common with this term over here? This is going to be really weird because up till this point our GCFs have always been monomials, just a very simple single term. For the first time in our math career, we're going to say that our GCF is a binomial. I'm going to say that our GCF is the quantity x minus 7. That's what these two terms have in common. So I'm going to go ahead and I'm going to factor out my x minus 7 and now try to decide what's left. If I divide this entire first term by the quantity x minus 7, I am simply left with x squared. And then if I divide this second term by the quantity x minus 7, I'm left with minus 4. All right, now we can finally see the light at the end of the tunnel. We're almost there. But I'm going to simply ask myself, is this factored completely? And the answer is not quite. What you'll notice here, the second grouping happens to be a difference of two perfect squares. So I'm just going to bring down my x minus 7 as is. And then the x squared minus 4 factors into x plus 2 times x minus 2. And what I'd like you to do tonight, and this is brand new, I want you to put a little FC with an exclamation point there. And that's our stamp of approval, saying that this problem is factored completely. Not just factored a little bit, but factored completely. So think of this as your stamp of approval and your way of signifying that it is completely done. Our second example here for factor by grouping starts off with 3x cubed minus 6x squared. Then we're going to say minus 27x plus 54. Again, some of the characteristics that I want you to notice is that this polynomial contains 4 terms and there is not a single GCF for all 4 terms. And what we're going to do is we're going to put our focus on just these first 2 terms and ask ourselves, what do the first 2 terms have in common? I would say that their GCF is going to be 3x squared. If I divide the very first term by 3x squared, I'll be left with x. And if I divide that second term by 3x squared, I'll get minus 2. Okay, shifting gears. Let's look at the third and the fourth term here. What did those 2 terms have in common? Well, you might have to play around with these a little bit. You might be tempted to say 9, in fact, but it's not. 9 is a common factor, but it's not the greatest common factor. We're going to end up factoring out a minus 27. That's the biggest number that divides evenly into both those terms. If I divide the first term by negative 27, I'll get positive x. And if I divide that last term by negative 27, I'll get negative 2. Okay, here's where it gets fun. As we mentioned in the last problem, we're asking ourselves, what does this term here and this term here have in common? And for the first time in our math career, we are saying that the GCF is a binomial, in this case x minus 2. So I'm going to factor out my binomial, and then I'm going to ask myself, if I divided that first term by the quantity x minus 2, what would I be left with? I'm going to say 3x squared. And if I divided this entire second term by the quantity x minus 2, I'd be left with minus 27. Now at this point, you'll notice perhaps that I've snuck in a little bear trap here. We are factored but not factored completely. And what do you see hiding in this quantity right here? Perhaps you see another little itty-bitty GCF of 3. We're going to factor out the 3, and technically I could put the 3 here in the middle of those two sets of parentheses, but I'm going to pull that 3 all the way out front and put it up here. So I'm going to say 3 times the quantity x minus 2, and now, let's see, 3x squared divided by 3 gives me x squared, and 27 divided by 3 gives me minus 9. And again, ask yourself, is this problem factored completely? Question mark. Not quite. Perhaps you noticed the difference of two perfect squares. X squared minus 9 is going to turn into x plus 3 and x minus 3. Whew! That was a workout. I think we're going to need to call a timeout and go get some water. Whoops, I almost forgot to put our stamp of approval here. Yes, this problem is now finally factored completely. There's our little stamp saying we have confirmed that it is indeed factored completely. All right, let's go get one more. Our third example, the directions simply say solve. Instead of factor completely, they're saying solve. And you'll notice that with a keen eye, you'll notice a subtle difference is we now have an equation. We have this little equals 0 at the end. So not only are we going to do everything we did in the previous two problems, but then when we get to the end, we're going to start to tee it up and identify the roots, aka when does this polynomial cross the x-axis. Now, in fact, just a little tidbit here. The highest exponent in this problem is a 3, which means we call this a third-degree polynomial. And a third-degree polynomial is expected to have 3 roots. So those are our expectations going into the problem. For instance, a quadratic equation. The biggest exponent on a quadratic is a 2, and therefore we would expect all quadratics to have 2 roots. Okay, here we go. Factor by grouping. What is the GCF for these first two terms? And I would say x squared. We're going to pick up the pace just a little bit here. If I divide the first term by x squared, I'll get 4x. And if I divide this second term by x squared, I'll get minus 5. Moving on to my third and fourth term. Their GCF, I'm going to say, is a negative 3. If I divide the first term by negative 3, I'll get positive x. And if I divide that last term by negative 3, I'll get negative 5. Still setting it equal to 0. Little details like that are going to make a big difference. Oh my goodness, I forgot my 4 right here. Oh, we almost had a train wreck. We almost had a train wreck. That's a good reminder from earlier. We said that the binomial in this set of parentheses and the binomial in this set of parentheses should be identical at all times. Okay, now, if we look at this term here and compare it to this second term over here, what do they have in common? Well, we have a new GCF, happens to be a binomial, and that new GCF is 4x minus 5. If I divide this first term by the quantity 4x minus 5, I'll get x squared. And then if I divide the second term by the quantity 4x minus 5, I'll get negative 3. Still saying it equal to 0. You may be wondering, is this one factored completely? I would say yes. The x squared minus 3, you're almost tempted to say it's a difference of two perfect squares, but unfortunately the 3 here is not a perfect square. So we are factored completely, and we are now ready to tee this up. So this, from everything I do from now on, is going to be completely new compared to those last two problems. So first of all, I'm going to say the quantity 4x minus 5 is equal to 0. I'm going to add the 5 over, say 4x equals 5, and then last but not least, I'm going to divide by 4, and I'm going to say x equals 5/4 is my first root. Second quantity, x squared minus 3 is equal to 0. I'm going to add the 3 over, and now I'm going to take the square root of both sides, and here's a really key detail. We're going to say plus or minus radical 3. So you'll notice we do indeed have 3 roots, and let's identify them. The first root is 5/4, the second root is negative radical 3, and the third root is positive radical 3, and we could juggle those 3 roots and put them in any order that we want within the solution set notation here with these squiggly brackets. We have now officially solved this polynomial. Well, ladies and gentlemen, we've just discussed our factor by grouping. I hope you feel somewhat comfortable with the technique, and if you have any apprehension whatsoever, we'll take care of it in class tomorrow. Good luck.